Hello AP Chemistry and welcome to the last of the chapter 15/17 lectures where we talk about the last, like literally randomly selected topics from chapter 17. So first, common ion effect, right? So this goes hand in hand with what we've already been talking about in terms of Q and in terms of Le Chatelier's principle, right? Which says that if we look at what the wording for the common ion effect says, right, is that, so for example, calcium fluoride is less soluble in a solution that contains either fluoride or calcium ions, right? Which makes sense because that's literally what we talked about in chapter 15, right? In terms of Le Chatelier's principle or even a QK analysis, whichever one we want to do, right? So let's say if we have this system at equilibrium and if we increase the concentration of that, then obviously, right, the system is going to move in this direction, right, creating precipitate, decreasing, right, the amount of calcium ion that is dissolved, right, which makes sense, right? That's what we talked about already, right? And the common ion effect is just the formal name for this particular scenario, right, where this graph puts that into perspective graph form, right, where if we have a solution that contains fluoride ion, then the solubility of fluoride goes down as the concentration of fluoride goes up, which we just said, using Le Chat's principle, which again, we've already talked about, right? So that shouldn't be new or a surprise. Now, how that plays out in terms of math problems, right? Let's say that we have some manganese 2 hydroxide with that KSP, right? And we would like to calculate the molar solubility, right? Where again, the molar solubility are the X's, right? In a solution that contains some hydroxide, right? So note, common ion effect, right? So what we're going to do is we're going to just start by writing the reaction, right? And here we should note, again, that the molar solubility being the X's really means we're looking at equilibrium concentrations, right? So if we're trying to find equilibrium concentrations and we have a K and we have some other information, right? Really, we should be thinking, let's set up a rice table, right? That's going to help keep us organized, right? KSP problems tend to be relatively straightforward, and so it's possible that you'll look at a couple of these and decide rice tables are more work than they're worth, and that's fine. You do need to still show all of your work somehow that's clear or include a few words about how you got what you got, right? But anyway, so let's go ahead and start with a rice table. So we got some of this, and we got this. And so there we have that, right? Obviously this is irrelevant, so we will omit that, right? And then we have our concentrations here. So we are saying that the solution already contains 0.02 molar sodium hydroxide, right? So this is 0.02 molar to begin, right? And this is 0, right? So here we're going to dissolve some more, right? And here we'll dissolve some more to some extent. So here we have this and that, right? And that's our KSP value, right? So then we're just going to set that up, right? So 1.6 times 10 to the negative 13th is equal to X times 0.02 plus X squared. And then we're going to solve for X. And X is the solubility, right? Because X is this Mn plus 2, right? Which is 1-to-1 reflection of the solubility of that salt. Yes? Does that make sense? And that would give us our answer, right? Okay, and so here is the last problem for this section. Does a precipitate form when we mix some sodium fluoride with some calcium nitrate, right? Our initial instinct would be to go ahead and just write a reaction for sodium fluoride and calcium nitrate, right? That's what we did last year a million times. And we would form some calcium fluoride and some sodium nitrate. And then we would look at our states and be like, well, these are solutions because they have molarities. This is soluble between the rule for sodium and nitrate. Oh, this one's a solid. And then you would say, duh, a precipitate forms. But then you would think, no, we are in AP chemistry now. It is ever so slightly more thoughtful than that, right? We would say to ourselves, oh, this is an insoluble salt. What is its KSP, right? And so we would find that. I believe it's in your guys' book, right? And the KSP for this is 3.9 times 10 to the negative 11th, right? And so that's its KSP. And so what are we really asking here? Right, this is a Q versus K problem, right? I want to know, is it going to precipitate? And here is where it gets a little bit here's where we just need to make sure we pay attention, right? I need to write out the expression that governs the KSP. So I'm going to write this out. So CaF2 is in equilibrium with calcium ions and fluoride ions, right? And so when I look at that, I'm like, oh, that's right. So when I say, does it precipitate form, and I'm just asking Q versus K, right? I know my KSP, right? So KSP is equal to 3.9 times 10 to the negative 11th, right? So I need to know, is my Q less than or greater than my K? And that will tell me which direction this reaction is going to go, which will tell me if I will actually see precipitation or not. Because if the concentration of my calcium and fluoride ions is too small, we might not get any precipitate of my calcium fluoride, right? I have to hit that solubility limit, right? So let's go ahead and figure that out. So that means in order to do a K, I've got to know the concentrations of my species to plug that in, right? So my QSP is going to be equal to Ca raised to and F to the second. So note that here, right, this is an example of where fluoride is coming from one species and calcium is coming from another. So it's not necessarily going to be true that the calcium and the fluoride ions are going to be related by their stoichiometry, right? My fluoride is whatever amount I get from sodium fluoride. My calcium is whatever I get from calcium nitrate, right? So let's go ahead and work that out. So if I have 0.02 molar and 0.05 liter, so 0.05 times 0.02, so I have 0.001 of this raised to the second. And for the calcium, I have 0.01 liters of 0.01 molar, which is 0.0001. And I'm going to get the product of this, which is going to be a whole bunch of zeros. Oh, nope, because we're not done yet. Nope, it's not going to be just a whole bunch of zeros. That would be too easy, right? These are moles, right? We got to divide these by our volumes, which is 0.06 liters. And this is moles up top. Now we solve for this, and this is going to give me my QSP, right? My QSP, once I work it out, it's going to be 4.6 times 10 to the negative 8th, right? Which I can then compare to my K. And what do we notice? Right. Q is greater than K, right? Which means my reaction is going to go which direction? If Q is greater than K, that means I have what? I have too much product, right? Which means we're going to go in the reverse direction. And in a KSP process, reverse direction means precipitation. Yes? All right. Next, finally, the last problem. A solution consists of 0.05 molar magnesium and copper. Which ion precipitates first as hydroxide is added, and what concentration is necessary? Okay, so we have KSPs, right? So really all we're doing is we are looking for what concentration of hydroxide is necessary, right? 1.8 times 10 to the negative 11th is equal to, right, Mg times hydroxide squared, right? So this would be 0.05 molar times my hydroxide, which would be X squared, right? And note here again, right, it's not like the hydroxide is not going to be twice that of magnesium necessarily, right? Because it's not coming from magnesium hydroxide, right? Over here, we would set up a 4.8 E negative 20 is equal to 0.05 times X squared, right? And we would solve for our respective X's. And for magnesium hydroxide, we get 1.9 times 10 to the negative 5th as my concentration. And then solving for the hydroxide for the copper. Okay, and for the hydroxide, we get 9.8 times 10 to the negative 10th molar, right? Which means that in terms of what concentrations are necessary, right? So these are the concentrations of hydroxide necessary for precipitation to begin, right? In terms of which of these will precipitate first, right? It will be the one that requires the smaller concentration, bearing in mind the way negative exponents work, right? So copper hydroxide will PPT first? Yes? All right, because it requires a smaller concentration of hydroxide ion. All right, so again, all of these problems from chapter 17 fall exactly in line what we've already been talking about in chapter 15, right? It's just a very specific kind of K that works in a very specific way, right? All of this is important because this is the foundation for all of the work we're going to do in the acids and bases unit, right? So make sure that it's crystal clear. Make sure if you have questions, you come see me sooner than later. All right, thank you for listening. Be good, and I will see you soon. Bye.